My name is Jack Tanner, and I'm doing a tutorial for ECE554 on how to use the filter design guide to create filters in ADS. So first, let's create a new workspace. Let's call it Filter Design Guide Tutorials. And from here, we're gonna ignore this. We don't need to create PCB technology for now. Create a new schematic. We'll just say this is FDGs, Filter Design Guide. Then from here, if you go to your left side under your parts window, you scroll to the bottom to your lower palettes, you'll notice you have a filter DG-all. This is where you're going to have your filter design guide options. So you have ST versus DT. This just means single-ended transmission line versus doubly ended. Single termination basically means that you have one end as a short or an open, whereas doubly ended transmission line means you have two different set loads that are not short or not open. So for our purposes, we'll do a doubly ended. Let's do a low pass filter. Among our options, we have low pass, high pass, band pass, or band stop. We'll do a low pass filter. And then if you click on this and you go to the top, you'll notice there's a design guide option. So under design guide, if you click on filter, click on filter control window, this will bring up our first window where we have the option to set some of the parameters for this filter. So we'll keep the impedances the same. We have set impedances for our source and our load at 50 ohms. First element's parallel. You can set that to parallel or series. Let's say a response type. Let's set it to Chebyshev so we have a sharper roll off. And then we have some options over here. So AP is the attenuation of your passband. Let's say we set this to 1 dB so that after I hit enter, you'll notice that it switches over to 1 dB drop off for your passband. That's basically your ripple. And then AS is the attenuation of your stop band. Let's keep that at 20 dB for now. As you increase this, you'll see it drops further and further. And the more you do that, the higher your order of your filtering reaches, which means more components and more complexity to your design. And then at the bottom here, we have the frequency of our passband. So this is going to be the edge. So these are the vertical lines represented on the y-axis. So for our purpose, let's say we're using Wi-Fi. This is a Wi-Fi transmission line. Wi-Fi channels go up to 2.4835 gigahertz. So let's set this to 2.5 gigahertz. Let's say our stop band goes to 3 gigahertz. So at 3 gigahertz, this is where it should roll off to 20 dB less. And you notice that gives us an order of 7. So if you want to decrease this, we can increase the frequency. Or if you want to decrease the order, we can also decrease the level to which we roll off. But for now, let's set it to 3 gigahertz. So now that we've done this, we first want to click design. This will create the design in our hierarchy. And now if you want to simulate it, we're going to go back up here to Simulation Assistant. And we can set our frequency sweep parameters. So for our purpose, we're just going to set them automatically 0 to 4.5 gigahertz, and we're going to simulate this. And this should, after a few seconds, bring up a new simulation window. So here we can see some of the values that we get. So S21 versus spec. S21 are the actual simulated values that we got. This is what we actually expect to get from the values, whereas the black line represented by spec is the target specification mask that we asked ADS to meet. And we can see on the right how some of the values differ. For example, our stop band edge that we set to 3 gigahertz is actually 2.85 gigahertz. And we also have some other important values like our delay deviation. So our delay deviation basically represents our group delay and how long the signal takes to travel through the system as a function of frequency. So these are our simulated values. But if you want to see the actual result, if we go back here, we click on it, we go down one level in the hierarchy, we can actually see the 7th order Chebyshev filter and all the design parameters and each of the values that we have for each capacitor and inductor. So now that we have this, let's say we put this into design and we notice some issues. It's not actually a 50 ohm match transmission line. It's a little bit off. And so now we need to edit it. Well, one of the options we have, if we go back up, we can go to our design guide, go to filter again, and then go to Smith chart. Then under Smith chart, if you double click that, will bring you to a Smith chart filter design where you can make some edits to it. So let's say I measure it on a VNA and we notice that I get an actual value of 25 plus J18. So let's say we put that in here. So let's use our load impedance on here to represent our filter. And now we can see this is where we're at. This is where we want to be. So we can make some changes to our filter and add new components on here to meet the specifications as needed. Let's say we lock our source impedance. Imagine that that's the actual load that we're trying to get to. That's at 50 ohms, so that's where we're trying to be matched to. And we need to make some changes. So something we can add a series inductor, and you can see as we move along here, we can adjust that value. Let's put it around here for now. And then we'll do a shunt capacitor. So we're just doing a 2-element match network. If you do it like this, we can adjust these components as necessary to get the matched result that we expect. And you'll notice that we have our network response in the top right that represents our S1 and S11 values. And we can see that after we set 2.45 gigahertz as our frequency that we're matching at, we have a good drop off at S11 at that value. So here we can also go down and we can see the specific values that we matched it to. So these are the values that we want to put into our design moving forward. Since this is kind of reciprocally designed, we want to set our capacitor or our inductor in series after the filter, and then we want to set the shunt capacitor, and we want to set actual real values. So you may have to adjust this filter moving forward since you're not going to find a 462 picohenry inductor. But this is how you can make some changes to it after you've seen the real values on a VNA. So that's how you can do a design in ADS using the filter design guide and the Smith chart utility.